Hi everyone. My name is Chandra, and today I'll be talking about some techniques that we've built for scaling formal verification of smart contracts to real-world programs. And this is work with my colleagues at Certora, Shelly Grossman, John Toman, Alexander Bakst, Samir Arora, and Mooly Sagiv. So smart contracts, if you haven't heard of them, are these programs that are used for doing financial transactions. And often these programs are deployed on blockchains like Ethereum, Stellar, Solana, and so on. So because these programs are often dealing with financial transactions, bugs in these programs can have really severe consequences. In the past decade or so, numerous tools have been proposed that are finding bugs in these programs, verifying these programs, doing fuzzing, and so on. In fact, there are so many tools that now there are dozens and dozens of surveys of those tools, and more of these surveys might be coming. So this is a pretty crowded space with lots and lots of tools and lots of techniques that are proposed very often. But unfortunately, even though there are so many tools out there, it doesn't seem like they scale to verification of real-world programs, especially when verifying complex properties. And so in this talk, I'm going to present one particular technique that we have come up with. And this technique helps us scale the formal verification to real programs. And they're built as part of this tool called the Certora prover that we've built. So the Certora prover is an automated SMT-based verification tool. It works at the bytecode level. So it takes as input a program in a high-level language like Solidity, Rust these days, and some others like Viper. And it takes a specification, and it just generates a verification condition and sends it to SMT solvers and gets a result. So as I said, the tool works at the bytecode level. So if a tool has to work at the bytecode level, then the tool should be able to reason about memory. And because we are working with SMT solvers, this is actually really difficult because often what it boils down to is that the solvers often have to learn a bunch of invariants about objects that may be completely unrelated to each other. And so to understand what that means a little bit better, I'm going to actually first give you a little bit of a background on what EVM bytecode looks like, and in particular we'll focus a little bit on the memory aspect, and then I'm going to explain the problem and then propose our memory splitting transformation, and then finally show some results. Okay, so in the EVM, memory is basically laid out as a giant single array of bytes, and I should be clear that for the rest of this talk I'll focus on bytecode generated by Solidity compilers. So you can imagine other compilers generating other kinds of bytecode, but this is focusing on different versions of Solidity. So it's just a big array of bytes, and unlike other languages like JVM or maybe even C, there is no way of knowing where allocations are being made. So there's no malloc or new or anything like that. So how does allocation happen? So basically, there is a particular value called, called the free pointer. The free pointer lives in a particular slot in this memory, and it's always the slot number 64. And so anytime you need to do allocation, you read the value of the free pointer. It tells you where the next free slot is, and you can allocate your object there. So as you can see, this is pretty low level, and there are no techniques that are available that can be used to infer a bunch of these high-level abstractions that you can easily do if you have languages like C or Java with explicit allocation mechanisms. So to make this a little bit more concrete, let's look at a particular program. So here we have a contract. This is Solidity code. It has a contract called C, and there's a struct called streams, and it has two arrays. And so a few facts. The pointers are all 32 bytes. And the array itself has a size. And when memory is allocated for the array, the first element is actually not the first element of the array, but it's the size of the array, which is actually really nice. And so each of the elements themselves are 32 bytes. So in total, you need 32 plus 32 times the size of the array. And so just to give you a visualization of this, so essentially what happens is, as I was saying, the free pointer is always at index 64. In hex, it's just 40. And you can see that the struct is made of two of those arrays, K1 and K2, and the first element of both of those is the size. And then ultimately, once the allocation is done, the free pointer is going to point to whatever is available at the end of the second array of the struct. Okay, so that's how memory works in this for EVM. So what's the problem? The problem here is that if the solvers, when you generate the verification condition from the bytecode, the solvers will have to figure out if different operations in the bytecode are referring to different objects or different addresses, or if those addresses can be aliased or not. So this is fine, actually, but the problem is that when you're dealing with real programs, you're going to have lots of reads and writes, and that will usually lead the SMT solvers to timeout. Or the alternative is that the SMT solver can just assume anything can alias with anything, but then you're going to have imprecise results. So what exactly happens when we actually generate the verification condition? So here I have a very simple example. mstore just means memory store, right? So it's just a store operation. We are storing x at location j and y at I, and we're just reading from g. And so when we generate the SMT queries, it's going to look something like this, right? So each of those m stores are going to get converted into these I if then else expressions. So basically, when you load the value from g, we're going to first check if I is equal to g, then we're going to return y. Otherwise, if it's equal to j, then we're going to return x. Otherwise, we'll havoc. And these are all following from the read over write axioms. So as you can imagine, this is going to grow in the number of accesses to memory. And so that's not really very good. So what we propose is we want to simplify the program before we generate the verification condition so that we don't have so many branches. So if this is what we have before, then ideally what we want is to be able to cut as many of these branches as possible so that we have a simpler query in the end. But how can we actually figure these things out? How can we simplify it? Well, the only way to do that is if you can somehow figure out that some of these addresses are not going to be aliased, right? So if you know that I and G are not the same, then you can actually remove it. So how do we do that? Well, first, to be able to do this kind of simplification, you need some kind of program analysis, right? Otherwise it won't be sound. So we're going to build a program analysis, but the problem with that is, as I said, everything is based on this reading of the free pointer. So in order to build an analysis, we first have to know where allocations are even happening. So we have an analysis. It is made of these three parts. The first part is an allocation analysis. What this does is it basically tries to figure out where allocation is happening. So it detects where objects are allocated. The results of that are sent into an initialization analysis. And this analysis checks that any object that has been just allocated is actually initialized before it's read from. And then finally, we have a pointer analysis. It essentially points, maps pointers to sets of abstract locations. For the rest of this talk, I'll actually mainly focus on the allocation analysis. You can read about the rest of the analysis in the paper. The reason I focus on this one is because if you don't have this, then the rest of the system doesn't work. And it's important to have the allocation analysis first. OK, so let's remind ourselves what we want to do. So the goal here is to detect new allocations. And remember that the only way to get a pointer is by reading the value of the free pointer, OK, that lives in that slot 64 in memory. So the first thing that comes to mind is, OK, well, what if we just treat every read of the free pointer as a new allocation? Seems like something we can try. So let's try that. So here we have A equal FP and B equal FP. So these are clearly aliased, so this is not going to work. So let's try something else. What if we try to use an SSA numbering? So what that means is that every read is going to get a new, like a fresh incarnation number. So in this example, this seems to work, actually, because there are no interleaving writes. So both A equal FP and B equal FP will have the same incarnation number. And so the analysis will say that A and B may alias. That's good. But this is actually not quite right. So the problem happens if you have some kind of condition in between those two lines. So say you have A equal FP, and you have some condition inside which the free pointer can be updated, and then you read the value of free pointer again. So because of SSA, the two reads are clearly going to have different incarnation numbers. But if you don't take that branch, they may still be aliased, right? So this is not right either. So instead, what the allocation analysis actually does is it actually does do the SSA incarnation thing, but in addition, it checks a property of the program. And if the program does not satisfy the property, then the analysis will fail and say that this program seems weird. So the property is called the definite write property. And so what it says, effectively what it says is, if you read the free pointer, you better update it after that read. And so more formally, it says that a read under some incarnation I must reach an update of the free pointer without any interleaving updates of the free pointer. So going back to that program that we saw, so here we have the read of the free pointer at a location B, so at B equals FP. We can't say for sure that it's updated because it does not satisfy that, because if the condition is false, then the branch won't be taken, and so this update will not happen. And because of the fact that this definite write property is violated, the analysis is going to fail and say that, well, this program doesn't satisfy the property. However, if you did have an update of the free pointer before the condition, things would be fine, right? Because we know for sure that FP has been updated, so A and B will have different incarnation numbers, but at the same time, it also means that we can confidently say that A and B are not going to be aliasing. One other thing about the allocation analysis, so if you actually move that free pointer update from before the if to the after the if, this is actually also going to fail. So the analysis does not like this, and that's for a different reason. So it's necessary for the free pointer's value to be always increasing. And if you have the free pointer update at the end of that condition, it's possible that somebody can actually reduce the value of the free pointer, and that's going to break a bunch of invariants. So the allocation analysis is not going to allow this. So overall, in summary, the allocation analysis essentially assigns these abstract locations to different free pointer reads by using this idea of this SSA incarnation number. In addition, it checks a couple of other properties. So the first property is it checks that the program satisfies this definite write property. It also checks that the free pointer's value is strictly increasing. And another thing it does, and I didn't get to it at all this time, is it does some lightweight pattern matching over the program itself to infer the shape of the object that was allocated. So it can detect if it's a struct or if it's an array or something like that. And as I said, the remaining analyses are in the paper. The paper has quite a bit more. So if you're interested in the Greek, it's in the paper as well. And there's also some coverage of related work. So there are some other papers, in fact, that have done analysis over Ethereum memory. So if you're interested in those, we discussed those in the paper. I now want to go back to the original problem that we started with. So remember, our problem was that we wanted to speed up SMT solving. So from that, we somehow went to this program analysis. So why did we do any of this? The reason is that we want to be able to simplify programs, and we want to do it soundly, right? So the analysis is designed so that we can simplify the program before we generate the SMT queries. And so here, I'm not expecting you to read the code on the right. That's just a representation of the bytecode that we work with. But the highlighted parts show what exactly happens at the end of all that analysis and everything, right? So you can see that on the left, there is a single array called mem. And after the analysis is done, you can actually rewrite the program to use different arrays for objects that you know are definitely disjoint objects. And so the consequence of this is that ultimately, when we generate our queries in SMT-lib, we have fewer branches in the IT expressions. OK, so now I want to talk about some results. So our goal was to, again, speed up SMT solving when doing formal verification. So to evaluate the system, we took 229 real-world benchmarks, and we ran formal verification on them with and without the memory splitting transformation. And so each of these benchmarks is actually a verification task, which means that there is a program in Solidity and a corresponding specification that comes with it. And so we ran our verification tool on those. And so points above the red line are good. So you can see here that in many cases, we are able to speed up SMT solving. But the most notable result is the number of timeouts that we solved. So the Certora prover is actually an industry scale tool. We have people who come to us with their code and want us to verify it. you can't tell them that our solver timed out, so we can't prove your property. So it's really important for us to be able to resolve these kinds of timeouts. And so the fact that the analysis and the transformation helps with that is really, really important. There's more in the paper. So we discuss how the benchmarks were selected. The paper also reports on the total number of partitions we were able to produce for each of these benchmarks. So remember, we are breaking down a big array into smaller arrays. So how many of those splits are happening, that's reported. We also have a comparison in the paper with another tool called Helmus. So Helmus is another verification tool people use for checking high-level properties of smart contracts. And so we compared against that as well. And finally, here's an interesting side effect of all the work that we've done. We did not expect this to happen, but turns out that because we implemented all this analysis, we were actually able to find a bunch of bugs in Solidity compilers. Our goal was never to go looking for bugs, but because we built the analysis and we have this trust but verify approach, where we verify whatever the Solidity compiler says it's doing, we were able to find a bunch of violations of some properties, and we reported them to the Solidity team, and they've all been acknowledged and fixed. So that's my talk. So we presented a memory splitting transformation that speeds up SMT solving, applied to smart contract verification, and we also found some interesting bugs in compilers. Thank you.
Hey, thanks for the talk. My question might be naive. So I guess like how general this approach is, like the Solidity increase the free pointer, but what if for the other types of memory management systems, like do you provide other types of optimization there?
Yeah, so I think the question is how common is it for the memory to be allocated this way, bumping the free pointer, right? And if we support other memory allocations. So for Solidity is one of the most popular languages that are used in this space, and every version of Solidity, like this is how they do it, right? So it would be surprising if this suddenly changes, or if suddenly they decide that they're going to do something else. We support from like some of the oldest versions of Solidity, like 4.2 or something, up until the most recent ones. And this seems to be applicable to pretty much all of them. We actually also support Viper. So Viper is another language that generates Ethereum bytecode. But I'm not actually sure how they're, if they use the same mechanism.
Yeah, so the goal of your analysis is to separate the monolithic memory into different memory objects.
Yes.
And the reason why it works in C is that if you have a pointer to a specific memory object and you do a buffer overflow, you will not point to another memory object because it will be an undefined behavior. Mm-hmm. And you don't have this property in your virtual machine. And so I was wondering how you deal with this issue.
So if the free pointer's value overflows, is that the question?
Yeah, if you have a pointer to a memory object that was allocated and you have a possible buffer overflow, then you'll be pointing to another object, mm-hmm. which is valid in the low-level semantics that you have, where it will be a undefined behavior and a buffer overflow in C. And so how do you account for this problem?
So the question is, if the increase of the free pointer is now suddenly part of the allocation of a different object, so how do we?
I think the question is about whether you could read from the free pointer and then do pointer arithmetic. So all of a sudden you're going to be pointing to a different object or something like that.
Yeah, exactly.
So you can do that. I think we strictly are always analyzing code that is generated by the Solidity compiler, and the compiler-generated code will likely not do this. Okay. But it's possible that inline, in this space, it's actually possible for people to manually modify the free pointer and do arithmetic on top of that. I think that we will probably not be able to handle that.
Okay, thank you.
Yeah.
Hey, great work. So I wanted to ask something regarding the compiler bugs you found. Were you able to have like to run analysis that were able to find the impact of these bugs in real-world contracts, like at scale? Was it something that's easy?
So this happened in not actually in bugs that I showed in the table, but as I mentioned, there's other compilers, like there's a Viper compiler, which is, Viper is another language. And we actually found a bug in, well, there was a known bug in the Viper compiler that did lead to some very severe consequences in like, you know, in the DeFi space.
Yes, yes.
We didn't find it because of the, this analysis, but it's definitely possible that these bugs do have real-world consequences. Our bugs were fixed before they were exploited, so hopefully, you know, nobody suffered from them.
Okay, thank you.